Okay, so digital signals. Digital signals, and I think you've already sort of seen this as we've gone through. Digital signals have a high or a low, and that's what we meant before by discrete signals. There's a high and a low. And that high and low can be described in multiple ways. So first of all, it can be described as a voltage. When you describe a high and a low as a voltage, typically the high is 5 volts and the low is 0 volts. You can always also describe it as a true-false, where the high is typically true and the low is false. You can look at it in terms of on-off, where the high value is on, the low value is off. And then in the next lesson, we're going to see that we can describe it in binary as a 0 or a 1. The high is a 1, the low is a 0. And I draw my zeros like this so that it's obvious it's a 0 and not the letter O. So you'll see that a lot, and that's why I do it that way. Alright, so we've been through the anatomy of an analog signal. Let's go through the anatomy of a digital signal. Okay, so a digital signal looks like a square wave, like the example that I showed you earlier on the analog signal square wave, and it was analog because it had negative values, and we know digital doesn't have negative values. They're also described as clock signals. You've done this a little bit already. In 116, when you looked at the 555 timer, you created a clock signal that allowed you to switch the inputs back and forth without having to actually create a switch and manually turn it on and off. Digital signals can also be periodic or non-periodic. So periodic would mean it has a definite period with a cycle happening every certain number of seconds. Non-periodic means the highs and lows aren't cyclical. Okay, so let's look at this picture here. So we're going to paste that in there, and we're going to do the same thing that we did with the analog signal and discuss some of the terminology that we use in describing those signals. Okay, so a digital signal, just like an analog signal, can have an amplitude. But we don't have a peak or a peak-to-peak amplitude. There's only one, so that's the one we deal with. For a periodic signal like this one, where you have a time high that is the same every time, the period would be the same as it is for an analog signal. It's the time for one complete cycle. And we still use the capital letter T for that. And then again, of course, the frequency is going to be 1 over whatever the period is, the number of seconds for one cycle. Okay, a couple other terms that you don't see in the analog world. When your digital signal is at a high, or 5 volts, we call this time high. So it's the number of seconds that it's at a high value, or a 5 volt value. Then we have this period of time where it's at 0 volts, and surprisingly enough, it's called time low. So it's the time that it's at a low value, at 0 volts. We also have what's called a rising edge or a falling edge. So this cycle, this signal would become high and then go low, and then go high and then go low. When the signal goes high, We call that a, whoops, not that, rising edge. And when the signal goes low, we call that a falling edge. Okay, one more term for you is the duty cycle. The duty cycle is the percentage of time that your signal is high. So I can have peaks here that last a very long time with low periods that are very short, followed by another long period of a high value. So the percentage of time for each cycle that it stays high is what is called my duty cycle. And it's designated, let me just do this. This we typically write as time high. This would be time low. So your duty cycle is the time high divided by the period. So that gives you a fractional amount of one cycle for which this time is high. So this one looks like it's probably about 60%. So we've got 10 divisions here. It's high for 6 of those divisions, so the duty cycle would be 60%. So we would take that fractional value and multiply it by 100 and indicate it as a percent. Okay, so let's go through a few of these definitions so you have them down. We've got amplitude. Amplitude is always 5 volts for a digital signal. Period. Time for one cycle. And it is measured in seconds. Frequency is the number of cycles in 1 second. Also the inverse of the period. Time high is just the time at 5 volts for 1 cycle. Measured in seconds. Time low is the time at 0 volts for 1 cycle. Also measured in seconds. Duty cycle. So it's the percentage that it's the percentage of time high for 1 period, which again is the equation that we wrote up here. Rising edge is the transition from 0 to 5 volts. Falling edge is the transition from 5 volts to 0 volts. Okay, so the activity that you're about to do allows you to use what's called an oscilloscope to measure some of these values for either an analog or a digital signal. So let's start with oscilloscope, what that is. Hopefully you've used this in science class at some point. So it captures and measures analog and digital signals. Okay, so you should have this picture here to put in your notebook as well. This is what an oscilloscope looks like when you're using multisim. So you can find the oscilloscope under the measurement tools. Same place you found the multimeter. You should be able to find the oscilloscope as well. It is running a Cartesian coordinate plane. And by that I mean it has an x-axis and it has a y-axis. The x-axis is time and the y-axis is voltage. Okay, the oscilloscope has a couple of features to it. It's got these two markers that allow you to place it at a certain point in the period on the signal. And then down here in this window is where you can view that information. So I've got two different signals here, and it's showing me the time between those two markers. So it's just an easy way to measure seconds. So this is your marker display. Then you have this part right here, which is your x-axis scale. So right here you can see it's 1 millisecond per division, and that's these large divisions here. This one is your y-axis scale. And here you've got 5 volts per division. So for each large division, that measures 5 volts. Okay, so let's look at how we're going to use that information from the oscilloscope to actually calculate some of these values. So the next thing I want you to add to your notebook is this cutout right here. I'm going to stick it over here to the side so I have room to work. Okay, so let's start out with determining amplitude of our signal. Remember, the amplitude is this value here. Okay, so there are actually no values that are on our graph itself. What we have to use are the x and y scale values. So I'm looking in the y direction for amplitude. So amplitude is at a scale of 2 volts per division. And I'm going to look at how many divisions do I have. I have 1, 2.5 divisions. So 2.5 divisions times 2 volts per division, because that's what my scale is, tells me that I have a 5 volt amplitude. Okay, period we can calculate from the x-axis. Period is the time for one cycle. So I just picked one that looked like it was at nice locations on my scale, so it'd be easy to pick off numbers. So again, I got to look at how many divisions I have. So in the x-axis for period, I have 1, 2, 3, 4 divisions. And then I've got to look at my scale to figure out what that means. According to my scale, in the x direction, that's 2 milliseconds per division. So I'm going to multiply that by 2 milliseconds per division. My division cancels out, and what I learn is that my period is 8 milliseconds. Okay, what about frequency? Remember, frequency is 1 over the period. I've already calculated the period, but remember, when I look at period, or frequency rather, it's in hertz, and hertz is cycles per second. So I need this 8 milliseconds to be in terms of seconds. So I can convert that. Milliseconds to seconds is going to give me 0.008 seconds. That's the equivalent. So when I calculate frequency, it's going to be 1 divided by 0.008. So my frequency is 125 hertz. Again, hertz is cycles per second, so that's why I need to have my period in terms of seconds when I do that. Okay, another piece of information that you might want is the time that your signal is high, or your time high. So to do that, I'm going to look at this value. This is my time high. So how long does that happen? So I'm going to do the same thing. I got to count divisions. So for time high, I have 1, 2 divisions, plus 2 of these smaller divisions. So I've got 5 divisions, small divisions, and 1 large division, so each one is going to be 0.2. So I've got 1, 2, 0.2, 0.4. So 2.4 divisions. I'm going to multiply that by my x-axis scale, which is 2 milliseconds per division. And when I multiply that out, I find out that my time high is 4.8 milliseconds. Okay, time low works the same way. Time low is this distance here. So for time low, I'm going to look at the number of divisions. So I've got 1 full division plus 0.2, 0.4, 0.6. So 1.6 divisions times, again, my x-axis scale, 2 milliseconds per division. So my time low is 1.6 times 2, or 3.2 milliseconds. And then, of course, once we know time high and the period, I can determine the duty cycle. So duty cycle is the time high divided by the period. And as long as I've got consistent units, it doesn't matter what units I'm using, so I'm just going to use it in the milliseconds units. So I've got 4.8 milliseconds divided by the period, which was 8 milliseconds. So my duty cycle is going to be 60%. So for 60% of the time, my signal is at a high value, 60% of a period. And that's about it. So you're going to do an activity here where you're going to get a chance to determine some of these values based on the oscilloscope measurements.